we'll get going because, as Jeremy said before, he can talk and he's a wealth of information. So there's probably a ton to get through. I'll say welcome to everyone for our first event for 2025. I hope everyone is feeling very rested and recharged for what will hopefully be a really fantastic year. And let's have our fingers crossed for some interest rates drops because I feel like everyone's just sitting on their hands at the moment waiting for that to happen. Anyway, today we're going to be joined by Jeremy Spencer from Positive Footprints. My name's Sammy Schweit. I'm one of the founding members of Sustainable Builders Alliance, and I'm also the director of Sanctum Homes. In the spirit of reconciliation, we would like to acknowledge the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respects to elders past, present, and emerging, and extend our respect to all Aboriginal and Torres Strait Islander peoples today. Today's webinar is part 2 of Making Net Zero Homes Sexy, or in Jeremy's words, mainstreaming net zero homes. If you haven't checked out part 1, jump on www.thesba.com.au and you can watch part 1 for free. And there's a whole bunch of other amazing webinars on there as well. Jeremy really doesn't need any introduction. I do like to think of him as a sustainable building superhero. He's a registered builder, he's director of design and build company. So you're laughing there, Jeremy.
Yeah.
Positive Footprints.
If only people knew the truth, Sam.
He is an award winner of too many awards to note. He sits on at least 100 boards and is one of the founding directors of Sustainable Builders Alliance. And he's actually the brains behind our roadmap to net zero, which can be found for free on our website. Today's webinar is proudly sponsored by one of our platinum sponsors, Wholesome. This is the 2nd year running that they've been a platinum sponsor for us, and we're really excited to have such a big company support what we're doing. Jeremy is going to be talking a little bit more about their EcoPack concrete range in his presentation. So I will let him talk to you about all the benefits that their EcoPack range has. Today's webinar will be a presentation, and please pop any questions in the Q&A down the bottom and we will try to get through them towards the end, although last time I had a massive list. So let's see how we go. So I'm going to throw it over to Jeremy. Mr. Spencer, take it away.
All right. Well, thanks, Ham, and thanks everyone for tuning in. Let's get stuck into it. I'm hoping that most of you have seen case study part 1. Part 1 was where we looked all about the operational energy use, and we basically at the start of that looked at both the operational carbon dioxide that gets released by a home, but also the embodied carbon dioxide that gets or equivalent greenhouse gases that get emitted through the creation of the materials that we build our homes of. And that's what today is really about, as to how to minimize the embodied carbon element. For those people who didn't see part 1, the case study home, this is the case study home, and this is its operational performance. As just a quick refresh, you can basically see there, this is an 8.6 star passive solar home. It produces more power than it uses. It's $500 in credit over the year and offsets 10 tons of carbon dioxide, basically by minimizing demand, by its welcoming in the sun during the winter, keeping it out during the summer, all that good stuff, and then putting on photovoltaics on top. And that's what we went through, how to do that in a cost-effective way, and how to use the SBA website, where the tools are located for you to also do that if you're not already. They are easy steps to follow relatively. The takeaway for me from last week when I saw this, it sort of changed how I see what a net zero home can be. A net zero home for me now, this is just a bit of a refresher from last week, is a resilient home. This house produces so much power during the day, but pulls very little from the grid at night. And effectively, this house could, there could be a blackout, and this house could go for days or weeks for most times of the year. Maybe not in the middle of winter, but most times of the year, this house would be producing enough power to run itself without being a big demand on the grid when the sun goes down because of its battery. I see net zero homes as potential energy hubs during such blackout times, where they can supply power to not only cars but neighbours' houses as well. I see net zero homes as low cost living lifestyles. So instead of the average $2,228 in Victoria for a dual fuel home, this house is $553 in credit. And that does not count the $300 a year or so that it saves by not being connected to gas, and also the $800 a year or so that it saves by charging its electric car. So these numbers start to add up to some handy pocket money. And lastly, a net zero home is a carbon negative footprint, offsetting 10 tonnes of carbon dioxide by putting excess power into the grid so that fossil fuels don't need to be burnt for that power to go into the grid, and in that way offsetting 10 tonnes instead of the average home, which creates 5 tonnes every year. All right, that was its operational performance. But this is where we got to at the end of part 1. What about true zero? Is this a true zero home? Is this a home that also minimises and accounts for its embodied carbon? And can we produce such homes? That's what we're trying to answer today. And we're going to do it by, first of all, I'm going to do a little embodied carbon 101, just so that we're all on the same page, what we're talking about and what's important to know as far as embodied carbon. I'm going to look at the structure of the home, and I've done an embodied carbon calculation on this home, so I'm going to show you how much embodied carbon there is in the home. And then we're going to look at the strategies that are on the website for minimizing embodied carbon, which ones were employed in this case study, and what quantified savings there were from that process. And then at the end, answer this question: did we produce a true zero house or not? And is that something that we could or should be aiming for? All right, bit to get on with. Embodied carbon 101, what you need to know. All right, so what you're looking at here is the standard life cycle of an average building. This is actually a standard protocol, an international protocol. When you're doing a life cycle analysis, these are the elements or the sections, how they section out the life of a home, from the creation of the raw materials, the transporting those to a factory to produce products, the transporting of those products to site and installing them into a building, then the use stage, where you've handed over the keys, the owners now use and repair the home, refurbish it as needed. Operational energy use and operational water use, those are outside embodied carbon. That's really in the operational energy use component, which we looked at in part 1. And then end of life. What happens to the home in its deconstruction? How much energy is used to transport it to a hole in the ground or for waste reprocessing, or potentially in section D to recycling as well? It says out of scope there, but in some protocols they do include that as well, where they know the future of the house or the building. Now, what do we notice from this? Couple things to notice. The page here says upfront carbon, and there's a bracket there saying upfront carbon, which is the A1 to A5. And this is what the Green Building Council say that we should be focusing on, the upfront carbon. There's a couple of reasons. The first reason is A1 to A5 is the lion's share of the embodied carbon over the life cycle of the house. So each one of those stages, when I'm talking about embodied carbon, each one of those stages, from raw materials, transport, manufacturing, each one of those stages requires energy to do that thing in that stage. And if you put all of the energy used throughout the life cycle, you'll get life cycle embodied energy. Each one of those energies, depending on the carbon intensity of the energy source that it's getting its energy from, will be producing carbon dioxide or equivalent greenhouse gases. If you add all those up, you get what they call embodied carbon for the life cycle of the house. Now, the World Green Building Council suggests that we focus on upfront carbon, which is the embodied carbon for that A1 to A5 section. That's the time when you hand over the keys of the house, if we're talking homes. And that's because, one, that is the lion's share of the embodied carbon over the life cycle of the house is in that creation stage. And two, because you can appreciate that as we look into the future of our buildings, it's hard to predict how long they're going to last, how much maintenance the owners are going to do on the house, and what's going to finally happen at the end of life. Is it going to be recycled? Is it going to be reused? What sort of recycling processes might there be in the future? We don't really know. It's a little bit more fuzzy. And so it's just you get better data in that A1 to A5 section. In fact, there's another little section there that says cradle to gate. And this cradle to gate information is is often supplied by manufacturers, or manufacturers have a handle on that. Because they use it to create things called environmental product declarations, which a lot of the bigger manufacturers are now starting to create to quantify the embodied carbon in their materials, from the creation of the material to the transport to the factory and the manufacturing to that product leaving the factory gate. So that cradle to gate information is quite robust, and it's usually reasonably easy to find for most generic products. Now, the other thing to know about embodied carbon, we looked at this graph in part 1, looking at what is the impact of embodied carbon. And just touching on it briefly again, this was a meta-study done by the University of New South Wales, Low Carbon Living CRC, and the Low Carbon Institute a couple of years ago, where they looked at studies from around the world that are trying to answer the question of how much embodied carbon is there in the average home or the average building, class 1 or 2 building, per square metre. And we came out with an average of 1.27. And this was, each one of those studies would have tens to hundreds of homes in them. Now, you'll see quite a variation within that. And you can see there's 2 rather tall columns there. And those variations depend on these, what they call boundaries, system boundaries, or how much information, to what extent, where do they chop off getting data for what goes into the home. For instance, are they including, as well as the timber and the claddings, are they including fixings and seals and bracings and glue? Are they also including deliveries to site and the power pole and the scaffold? Are they looking at the machinery that's running? And what about the builder's building and his computers and marketing that they do? And these broader concerns, are those also being included? And that's why you get such a big variation in the actual answers there. And that's really because this is still quite a new a new industry, this life cycle analysis industry, and the industry is trying to get its all tie down what its protocols and what data and what methodologies are going to be used. But as a rule of thumb, as a working rule of thumb at the moment, until I know better, I go for this. 1 square metre of house is approximately 1 tonne of carbon dioxide. So if you're not doing any calculations, but you just want to get a basic idea, that's not a bad one to use on site when you're looking at plans. Now today, I'm going to be using, I like this database. This is a free carbon coefficient database, which looks at products and the amount of carbon dioxide that they use, typically by weight on there. Now, I've worked with this database quite a lot for the True Zero Carbon Challenge, the Design Matters National True Zero Carbon Challenge, where we created a front end to work with that database and allow us to then run the challenge and produce reports. So I've run my house through this spreadsheet, and this is what we came out with. Well, this next section is all about the base case home. So this is what we came out with, but of 213 tons here, 213.7. Now, this is not the house as built. This is what the way I'm doing this presentation is to start with what I'm calling the base case home. The base case home is one that uses the standard materials in the Melbourne suburban environment. So most houses around here are built with new brick, and they'd be built with virgin concrete. And probably for the floors, we'd have carpet in the bedrooms, tiles in the wet areas and the living areas. So you can imagine this house, the actual house form stays the same, but where I'm just substituting in those materials. And the reason I'm doing that is so that I can show you as we go through this and apply some of the strategies to lower embodied carbon, how this relates to more standard construction. And on the report, once I've inputted everything at this 213.7 tons of carbon dioxide for this standard house, this is how we break down. We've got floors here. Floors is around about a bit over a quarter of the embodied carbon goes to floors there. And just to get an idea of this particular house and what's involved here, it's a reasonably complicated flooring system. We had a sloping block. We start up on the high end of the block with a slab on ground sitting on piers, a waffle slab that was. And then as the ground sloped away, the owners wanted the house to be all single level as they were elderly. And so we've got a brick strip footing, double brick over concrete strip footings, and running up the guts there, we've got little brick piers with I-beams over the top, which carries a Bondex slab over the top of that. And then there's also one other concrete section, which is a slab on ground. We saw it in part one. This is thermally broken because this is actually on the outside of the house with a deck over it, and that was sloped so that we could try and stop what was a drainage issue on the site. We had water that would sometimes run down the hill and flood the house, and so we didn't want to create a deck. We wanted a deck, but we didn't want to create a deck with a space where all that water could sit and stagnate and need pumps and so forth. So we put a sloping slab to slope it away. Anyway, that's the flooring situation in this house. On top of that subfloor, for the base case home, for the actual home, we end up doing polished concrete, which we'll look at. But for the base case, this includes tiles to all the bathrooms. It also includes tiles to the living area and carpet to the bedrooms, is what would be a standard house. If you're going and looking at standard homes, that's probably what they would have. And then painted garage floor. Okay, and that gives us our embodied carbon for our floor of 60.4 tons. Walls, 55.3 tons. Again, a big quarter of the embodied carbon in this home. And these are probably pretty similar, for most homes. So if you're wanting to get a sense of how much embodied carbon and where it is in the home, these ratios are probably pretty similar in most homes. For the walls, we're talking about, we have timber framing throughout this house. That's standard. This house in particular, though, had some internal brick walls, which in reality, we use recycled brick, but for the base case, we're assuming that they would be virgin. And we're also assuming for the base case that it would have been brick veneer, so that we can see the difference later of changing it away from brick veneer. Then ceilings and roofs. In the software, I split those up because it's just easier to enter, because ceiling size and roof size is different, and you can have different materials on both. But as a group together, ceilings and roofs, this is our structure. We just have a flat framed roof throughout, 240 by 45 rafters. Can't remember if it was R4 or R5 that we got into that space. Plaster on the underside, metal ceiling on top. Pretty standard sort of construction there. Now this element here, these 4 elements, floors, walls, roofs, and ceilings, are what they call cold shell. So if you do hear this when anyone's talking about embodied carbon, Cold shell just refers to those things. Now, there's more things that happen in the house, and you can see that the cold shell in this case is about 2/3 of the embodied carbon. We've still got external works, typically not part of cold shell analysis, because external works can sometimes be very broad, sometimes they can be small, so often they just seem to be left out. And also this plumbing and cabinetry and sundries section. Now, that's quite a big section when you put it all together, and includes wires and pipes and lights and switches and plumbing and toilets and basins and basically all the other bits, cabinetry, all the other bench tops, all the other bits within the home. Now, as far as data goes, you have pretty good data for these walls, floors, ceilings, and roofs. But when you get to complex items like air conditioners and hot water systems, there just isn't the data. There's such complex machines. I was listening to a presentation from someone at Bosch, and they were saying, was it Bosch? No, it was Dakin. They were saying that in their aircon, there's over 2,000 pieces that come from all around the world, different places to be assembled. So it's very hard to get accurate figures on how much embodied carbon. So typically what the protocol is to look at how much the item costs and to apply a carbon intensity per dollar sort of factor. So you can take this for what it's worth. There's not as much volume in these things, but there's a lot more effort and like intensity, if you like, of putting the items in this column together. It's hard to know how accurate exactly that is, but we're just talking about give you a sense of where the embodied carbon is in a home. All right, let's get into, now we've seen what the house is, let's get into the principles to minimize embodied carbon and which ones we applied on this job, and then what savings we got for that. Now, on our website, step 2 is all about specifying for low impact materials specification. And it's all about embodied carbon. Halfway down the page, if you click on principles to minimize embodied carbon, you will get a list of principles, and those are the ones we're going to go through now. Of course, I recommend you later go back and if anything interests you, read it properly. There's a lot of links within all of these links to different resources on the internet, and a lot of tips in there. Okay, let's go through the principles. Principle 1, renovate rather than build new. So this was the original house. There's actually not much wrong with it structurally. It did, had the normal cracking inside. Maybe some of the floorboards were a bit bouncy, could have done with some re-stumping. It was dark inside. It wasn't laid out well. The living was at the front on the street to the right of the first picture, sort of on this side. And they wanted it to face more to the side and rear of the yard. The house also did, as I said, suffer from infrequent flooding. When it rained enough, you get water running down here, and those drains wouldn't do the job, and it would sort of come inside. So there were issues with the house. However, this house could have, if we had the right brief and the right owners, potentially it could have been fixed up. It could have been insulated. It could have been left pretty much as is. New appliances put in, and we could have got that one humming as well. And that, of course, would have had a lot less embodied carbon added to it. But in this case, the owners have been living there a long time. They had reasonable idea of how they wanted to interact with their yard. And by the time we started looking at taking down external and internal walls, replacing linings inside, stripping it to get insulation in, when you start doing that process, in this case, it just came to that stage where no, it just didn't make any sense to try and keep the existing structure, which is a shame. And in a lot of instances, we do renovations as well. And, half time we do renovations, and we are able to just, extend out the back and put that new living area and, connect it to the existing house. It just didn't work in this case. So no, this, we weren't able to do strategy number 1, but it was not particularly applicable in this case. Okay, principle number 2. But where you can, of course, every square meter of house you save, approximately 1 ton of carbon dioxide you've saved. So always hold that in your mind. Where you can keep something, I would suggest you try and do it. Always have that conversation anyway. Principle 2, avoid building bigger than you need. So the clients came to us, they wanted to install the Ordinary Miracle, one of our Carbon Zero series. And in their case, they needed to flip it, but they flipped it and also increased it a little bit. So the original Ordinary Miracle, 180 square meters plus carport. They enclosed the carport, made it into a bigger garage, and did a bit of pushing here and there on the walls. And before you knew it, we're at 263 square meters. Now, this is how they liked it. They had some quite set ideas, but as a principle, we want our homes to be as efficient. We want the spaces that the clients want, but we don't need more than they want, if you know what I mean. We want to have spaces that work without having what I'm coming to call flabby homes. I'm finding that's a really useful term. If you're trying to maybe talk clients down a little bit, you can start talking about designs a little bit flabby. No one likes flabby. So if I was able to potentially do it again, though the clients, we did have these conversations with the clients, and this is how it ended up, and that's just how it is. But I could see that we could quite easily take a scalpel to this and cut off 0.5 meter to 1 meter across the top there, maybe across that bedroom one, and maybe across the back of the garage. But it's horses for courses, and each clients are different. But if we could have done that, could have potentially saved 20 square meters or so out of this design. That's approximately 20 ton savings with our rule of thumb, and maybe $2,000 a square meter. Mainly, that's not our square meter price, everyone, but we're just taking out mainly floor area here. So, but that's a reasonable saving. 20 by 2,000, that's 40,000. If you do that on a project, all of a sudden you've got a lot of money to put into appliances and PV. So we weren't able to do it on this job, but that's the principle. Okay, principle 3, maximize volume to wall area. So different shaped houses can have different amounts of surface area to the volume that they hold. Obviously, a square or a rectangle has a pretty efficient amount of floor space to wall space. As soon as you add in a lot of courtyards, you end up with a lot of material for less volume of actual house insides. And so one way to minimize the embodied carbon is to minimize the amount of material in the house and to rationalize the space a bit. In our house, let's see, this is the outside of the house. Look, this is reasonably it's reasonably rational design. It does have a courtyard here. That courtyard, however, is facing to the east, facing to the winter sun, so to be a light court to warm up in winter when the shade sail is out of here. So I'd say this has a reasonable form factor and give it a bit of a tick for that one. But if you had a design that had lots of ins and outs and lots of courtyards and turnarounds, it might be something that you want to just discuss with the clients. It also obviously cuts down costs whenever you cut down wall area and the windows that would be associated with that. Principle 4, avoid unnecessary linings. Now, here's a lovely apartment shop from Breathe Architecture, where they've shown the off-form concrete. The general rule here is if you don't need a material and you don't put it in, then obviously less material equals less resources and energy use and embodied carbon where you can do it. It's not necessarily going to save you money. Something like this, I know in a domestic environment, takes a lot of communication with different trades to get their rough-ins nice and neat. A lot of them are not used to having their pipes and wires on show. So it can be done. In our instance, though, we did something that's maybe, well, in some ways is easier, and that is to simply take off the floor coverings against the base case house. In fact, our clients were quite eager to do as much polished concrete as they could. We used recycled glass from Schnipper Glass, threw that on for a happy slab throughout. Now, doing that saves more than you might think. Here we've got an assembly table of the different carbon intensities per square meter of different material finishes on surfaces. And we have a whole lot of tables like this actually on the website. I'll show you later where you click on to find them. But if you look at this one, carpet on underlay over board or slab, and tile on underlay, you can see the carpet has a really high embodied carbon, strangely high, you might think. That is partly because this iteration of the True Zero Carbon spreadsheet also included maintenance, and over a 50-year lifespan you might expect to change the carpets up to 3 times. So that's why the carpets they're quite high to begin with, but of course if you multiply by 3 they become quite a lot higher, whereas polished concrete's going to last for basically the lifespan of the house. Might need a rebuff, but that's minimal energy use. Now, so doing that strategy, minimizing that material, which we did on this house, we gained polished concrete throughout minus 6.7 tonnes. So this is a little tally that I'm setting up, and as we go through, if there are any strategies that we did do, I'll show you what sort of savings we got putting it through the EPIC spreadsheet there. Principle 5 is reuse materials from demolition. Now in this case, from demolition in new house. This is actually not the house this time, but we often do reuse bricks, and that is what we did in this case. Other things you can, I'll go to that slide in a minute. Other things you can reuse, again, not this particular home, but just for this principle, this was a house where we tried to reuse recycled cabinetry and use that for the kitchen. Came out beautifully. Not necessarily a cheaper thing. In fact, usually it's not cheaper to try and repurpose cabinetry, but does cut down on the embodied carbon and can also look beautiful. Some other ideas where we've used old joists to make tables, old floorboards to make vanities. Once again, this is not a cost-cutting measure. It does potentially cut down on embodied carbon, but it also creates items which really tell a story about the old house and are sort of a lovely thing to put into the new house potentially. Anyway, something to consider, not to do every time, but you should always, when you're going through an old structure, if it's going to be knocked down, see if there's anything of value. Often we do have timber floors we put in, and I always look at the floors of any demolitions we do to see whether they're going to be nice boards when they come out, and as long as they're not glued down and they're in pretty good condition, we can usually take a little bit of time and take them out, and that's usually pretty much a cost neutral exercise. In this instance, it was the bricks of the house. We demolished the house, cleaned up 7,500 bricks, stacked them all on site. Each brick, by the way, every time you clean a brick, the embodied carbon in that brick is 1.4 kilograms of carbon dioxide that you save in not buying a new brick and just cleaning up the old brick. 7,500 of those, and you end up saving 9.9 tonnes of carbon dioxide. The other thing with brickwork is that it needs mortar, of course, to put it together. And if you search for cement, because cement is actually a high carbon product. If you search for cements that have minimal Portland cement or some Portland cement replacement, the Portland cement is the part that has the high embodied carbon element in the cement. If you choose ones with, in this case, slag, sometimes fly ash, which have a similar bonding mechanism, but they just decrease the amount of Portland clinker that's needed in that cement pack. And by doing that on this job, we're able to save another 0.4 tonnes of carbon dioxide. So we put that on our tally sheet, and it's starting to add up. All right, what's our next strategy? Oh, there's the fly ash. Okay. It wasn't fly ash, it was actually slag. That should say slag. Slag, by the way, is the leftover component from iron smelting. Fly ash is the dust that comes off the chimneys when they burn coal. Is the fly ash. This one was slag. Okay, principle 6. is if you don't have recycled materials already on site, you can obviously bring them in. This is another job that we did, but on this job, it was an old weatherboard and we were building a lot of reverse. This was reverse living. We had the living upstairs to try and get it out up into the sunlight. It was quite overshadowed on the ground level. And then we put in some reverse brick veneer there to give that upper floor a little bit of mass. Upper floors can often heat up and cool down very quickly. And that was just a way of making much more stable temperature upstairs. And again, timbers, recycled timbers you can bring in for decking, for stairs, for floors. They can look absolutely beautiful. I'd suggest if you haven't done this before though, you definitely go down and check out the lot, the packed lot that you might be getting to see whether it's suitable for your build and nice and even, and the grooves, if the floorboards are nice and clean, and the boards are the same width throughout and all that sort of stuff. But well worth doing. Especially if you do go to a lot of the salvage yards where they're recycling things, they will know where it's come from. You can often get a bit of a history and a story to recycled goods, which, owners love to tell later that their staircase came from so-and-so factory or wool shed or something. But in our case, we didn't bring in any extras. We simply recycled all those bricks. Okay, principle number 7. You can also get new materials with high recycled content. So if we're wanting to be a sustainable society, we really need to copy nature, and we have to start thinking circular. We have to start working out a way that the waste elements from our industries and our buildings become the feedstock for new industries. So wherever you can, or wherever we can, I like to try and choose materials with recycled content already in them, because that helps start that process of that circular economy that we need to get to. It can't all be just a one-way trip to a hole in the ground. That sort of society won't last, thousands of years. Here are some materials. We didn't use all of these in the bill. We did use EcoDeck up here. EcoDeck, recycled PET into that, 45% I think, and waste timber sawdust goes into those. The EcoBase, Alex Fraser EcoBase, that's crushed concrete and crushed brick, but they crush it quite fine, and you can use it for laying pipes as similar to 7mm stone. You can use it as pavement base as well. Fletcher insulation, 80% recycled glass goes into that. These are island blocks. We didn't use these on this particular job, but island blocks, 37% recycled content, and they're carbon neutral. So I won't go through all of these materials, but you should always keep an eye out for interesting materials, and a good place to start looking for them are on these links here at the bottom of the page, recycled material directories. You can find them linked through on the website as well. How much embodied carbon do we save, however? Well, as it says here, embodied carbon savings, if any, are impossible to quantify without an EPD. Now, what's an EPD, you ask me? An EPD is an environmental product declaration. I mentioned it before, but over the last 5 years or so, a lot of companies have started getting on board the EPD bandwagon, and they're doing this so that they can get green stars and to work out how much embodied carbon is in their products, typically that cradle to gate component of the life cycle. But it becomes a really useful way to get 2 EPDs, say of of a brick or of steel or of concrete, and you can compare the 2 EPDs. Look for, I won't go through it today, but look for the global warming potential factor, and you can sort of start to compare apples to apples, because the EPDs follow a protocol and have to be created by a third party and following a set criteria so that you can compare across EPDs. But if you click on using embodied carbon data to guide product selection in step 2, and then click on EPDs, you'll come to a section that explains EPDs. They're a little bit clunky to use if you don't know what you're doing. So this little area of the website will walk you through how to interpret and use EPDs. They'll also link through to epdaustralasia.com, which is the database of where all these EPDs tend to be stored. Now, on our particular job, we used a product with recycled content with EPDs, and that was Wholesome EcoPact. And that went into all of our piers and, piers here, and our beams, and our piers up the back under the waffle slab area, all were filled with Wholesome Triple Blend EcoPact Zero. And I'll explain what the difference is in a minute. When I look at their EPD, and this one may be a little bit old. This was back when they were calling it Virodex. It's now called EcoPact and EcoPact Zero. But what Wholesome has done, and quite a few companies are now starting to do this, is to work out the embodied carbon in their products. And so you can see here, standard concrete, we typically use 25 MPa or maybe 32 if we're polishing it, but for the beams and the piers, 20 to 25 MPa. Say it was 25 MPa, 358 kilograms of carbon dioxide per cubic meter. That's what it's telling me from this EPD. Now, instead of the standard concrete, we specified their T blend. It's now called EcoPact T blend, not Virodex T blend. Which is a triple blend. That T stands for triple, and that's got slag and fly ash. So they've taken out some of the Portland cement, or quite a lot of the Portland cement, and replaced it with slag and fly ash. And so instead of 358 kilograms of carbon dioxide per cubic meter that you order, it's now 215 kilograms of carbon dioxide per cubic meter. So that's a saving of cubic meter of 143 kilograms of carbon dioxide. Now that's just specifying triple blend. Now, if you go the next step and specify zero, you can specify EcoPact Triple Blend Zero. What they do, because they have calculated the embodied carbon in their product, they can then use Climate Active, which is a government program, to get an offset company to offset the remainder of their product, so that they're taking responsibility for the embodied carbon of their product. They've minimized as much as they can, and now they're offsetting the rest, so that what turns up on site is, is carbon free or without the carbon debt. So if you do go and choose the EcoPact Zero product, you effectively save that 358 kilograms per meter cubed. And what that meant was, on our site, just for the strip footings and the piers there, that was a saving of 10.2 tonnes, which is a lot just for a different specification on the concrete. Now, just specifying the triple blend instead of the zero, you get 4.1 just for going the triple blend, 4.1 tonnes of carbon dioxide saving. But it's a lovely feeling knowing that you're putting this concrete into the hole that is without the carbon price tag. Okay, so let's put that onto our tally board. Wholesome Triple Blend EcoPact Zero carbon neutral concrete to piers and beams, minus 10.2 tonnes there we've saved. Okay. Principle number 8. And by the way, I should thank Wholesome. I know Ham already did it, but it is great having you on as a platinum sponsor, Wholesome. And it is really as easy as just changing a specification on your plans, or ringing up and asking for EcoPact Zero instead of EcoPact for whatever MPa mixture you're after. So they made the process nice and easy, and big. You can do big savings with with just that step. All right, principle number 8. Choose carbon sequestering materials. So carbon sequestering materials are simply materials that grow, and as they grow, as a living plant grows, it just sucks in carbon dioxide, breathes out oxygen, all that good stuff, and the carbon from that carbon dioxide goes into the body of the plant. Typically in wood and plant material, once you've dried it out a bit, half of the weight of that material is carbon in that material. So the reason that carbon sequestering materials is good, there's two basic reasons. One is that it's not something that has been dug out of the ground and then melted or fired. So it's typically lower in embodied carbon, just its normal upfront embodied carbon is usually lower. But also it has what they call biogenic carbon. That's the carbon that's it's absorbed within it, like it's got this like carbon bank inside it. Now, there's a lot of discussion in LCA circles, life cycle analysis circles, of how one should treat this what they call biogenic carbon. Should it be a credit? In some systems, it's a credit against the embodied carbon in the structure. But typically in Australia and in most places, what they're doing is saying, no, we can't really give it as a credit because at end of life, one, it comes out of the structure and the material might be burnt or it might be broken down in a way that it releases, methane into the atmosphere or carbon dioxide back into the atmosphere. And also it leads to some perverse outcomes. If you allow it, you could have a concrete bunker sort of building and then just start slapping on timber on the outside until it's carbon neutral, which is not the right signals that we want to send. So typically these days in environmental product declarations, what they're starting to do is list it as a different line item. So you'll have the embodied carbon and you'll also have the biogenic carbon as a different item. So you can start to see how much biogenic carbon is also in that structure as, a different metric to perhaps give credits on later. And here are some nice materials. We often use bamboo for floors and cabinetry. Cork we've used before. Strawboard we're using on an upcoming project. The others I haven't had the luck to use yet. I know that Ham's used hempcrete, and I no doubt people on this call have used some of the others. So good on you. I love them. On our job, what do we use for carbon sequestration materials? Well, timber that everybody uses, this is standard throughout the industry anyway here in Victoria, is to use pine framing. That does actually sequester some carbon. We used abodo cladding on the outside. We used bamboo for one of the feature doors in here. But I'm not claiming any of the biogenic credit in this little calculation here. If you did want to claim it, like I said, in an item like this, it's nice and dry, half the weight will be carbon. So let's say this door was 100 kilograms, 50 kilograms of that is carbon, if you want to know how much carbon is in there. These are sort of a rule of thumb way of working it out. Now, to absorb that carbon, the plant has breathed in 3 times that much. In a carbon dioxide atom, carbon is one of the elements, and then there's 2 oxygens, that's the dioxide. So carbon is approximately 1/3. So you multiply it by 3, 50 kilograms times 3, there's approximately 150 kilograms of embodied carbon has gone into that, if you want to think of it that way, into become biogenic carbon, I should say. But in this instance, we're not including it as part of our tally. But if you did want to add up all the carbon in your house, that's basically how you'd do it, or the biogenic carbon. And that does bring us a little bit to just the idea that embodied carbon isn't the only thing when you're looking at materials. When you're looking at trees in particular, I know Paul Ha, one of our webinar guests in the past, had a great line that trees are the most environmental and the most unenvironmental things that you can possibly put in your home, depending on where they are sourced. And so there are broader sustainability criteria that you should be considering. There's a whole section on that in the website, and some great resources just on general sustainability of materials, and it's actually part of the website I hope to build out in the future. But one of the elements here, if you are looking at biogenic sources, this timber products, if you want to make sure it's good wood, you can click on that, and that opens this document. This was created for Mullum Creek by Paul Ha. And it's a really great place to start if you're looking at sustainable timber. It goes through a whole lot of different timbers and products and what they can be used for, and gives you a nice list of sustainable options. Anyway, something to check out if you haven't already. Okay, principle number 9, choose local rather than distant, but consider transport type. So obviously the further something comes, all else being equal, it's going to have more transport embodied carbon in it. But it does matter how it's delivered to you. If we look at this little graph here, this is grams per ton per kilometre. So if we're looking at air freight, it's really high in embodied carbon per gram of stuff that it takes, because it can't take very much and uses a lot of energy to take a little amount. Whereas if you've got a very large container vessel, it's actually quite low per grams of carbon dioxide per ton of material transported per kilometre. And if you look here, trucks are surprisingly high, and it can actually be the case if you're trucking something down from, say, Queensland to Victoria, where I am. That could have more embodied carbon in transport than the same product if it's transported by container from, say, New Zealand. It might be lower in embodied carbon. Now, of course, if there were trucks taking it from the North Island to the South Island in New Zealand, and that needed to be added on as well. And while this is a rule of thumb and something to consider if you know the transport of what's happened with the transport of the material that you're wanting to buy, in general, we don't have information about the actual transport embodied carbon unless it's on the EPD. EPDs will have it if it's been, if they've gone into that part of their A, B, Cs and Ds in the transport parts. So you can look it up there. But in general, it's a rule of thumb to consider. How do we use it in this particular project? I said before we use Fletcher insulation. One of the reasons I use it, one, it's a good insulation, but also it's produced at Dandenong, which is quite local to me, and being quite a voluminous product, I don't want to truck it in too many trucks too far. So now I can't actually use it. Carbon savings, I reckon there are some carbon savings of using this versus one that, is being imported, but I can't point to it and say how much. So it's not included in this tally. Now, I've mentioned quite a few interesting products, and I'd be remiss if I didn't point out that SBA have a tool for recording interesting products. It's our environmental and low carbon materials specification sheet. And this is something that I've been using for years just to record interesting materials that I come across. And it sort of separates it out. I don't know how well you can see it there on your screen. Maybe that's a little bit bigger, but separates out into the different building elements, products, contact details, web links, environmental benefits and notes. And it's just a way of keeping together and growing an environmental specification over time. And when I find a material that looks interesting, I stick it into this specification sheet, and then I might trial it in an appropriate project. If it works, if it's not too hard to install, if it's convenient to use, if it's not too much, then it stays on the list. If not, it gets crossed off the list. But what you'll find if you use this sheet or something like it is that over time you'll be able to build up quite a comprehensive specification that you just use over and over again because the things work. So I recommend download that if you don't already have something similar. And remember, what you specify grows the market and in time becomes the market. So we should be trying to put those hundreds of thousands and millions of dollars of product that we keep specifying year on year into the greener industries so that they become more common. All right, principle number 10, choose low embodied carbon materials. But how do we know what is a low embodied carbon material and what isn't? Two ways. The first way is that there's a couple of rules of thumb. One is that thinner products have less embodied carbon than thicker products. So for instance, here you can see this is a different home, but we do have metal cladding on the Ordinary Miracle series and on the house in this study. Steel is pretty high in embodied carbon per cubic meter, but per square meter, because this is only 0.46 millimeters thick, it's quite low in embodied carbon. So thinness and thickness matter. The other thing to consider is, has the product been fired or has it been melted in its production? Those are those products that are typically have higher embodied carbon. So those are two little rules of thumb. The other thing is that modular construction, you see how this house is sort of set out in modules, it typically will mean that there's less wastage on the and offcuts, which also, if you have less wastage, again, you use less materials and so less embodied carbon as a general rule. So that's one way. The other way, if you want to get into the nuts and bolts and have a little bit more direction than that, again, you can click on using embodied carbon data to guide product selection. This time, click on the EPIC database, and I've already created some tables of materials per square meter, converted them from, in the database itself, it's usually per weight. I've converted it per square meter to make it something easier to consider. So R2.5 insulation, for instance, I was sort of surprised when I saw these two. I always thought rock wool and glass wool were pretty similar sort of products. Rock wool has a fair bit more embodied carbon to it than glass wool. Has some advantages, but that's interesting to note. And these are just interesting to read through so that you have a sense when you're putting and choosing and selecting products, which ones have low embodied carbon, which ones have high embodied carbon. Here's some flooring types. You can even start putting them together with different subfloor assemblies, which I've put together there. Claddings, you can see aluminium sheet, very high in embodied carbon. Basically, it takes a lot of electricity to make aluminium. Whereas rendered FC sheet, it's quite a thin product. It's an air dried product, so less embodied carbon in that. And structural timber and roofing. You can look at those yourselves. If you continue down on that particular section though, you get something that's maybe even more useful, and that's where I've put together typical assemblies and given them per square meter. So you can see how much embodied carbon is in a typical assembly, and typical assemblies are different cement replacement percentages as well, whether it's timber subfloor where the cement is just under each stump, or for raft slabs as well. So that's for subfloors. I won't go through these, but I'm just showing you what's on the database, on the website, so that you can interact with it and learn yourself. When I first started out, I was referring to similar tables by a guy called Lawson. Had written a book about embodied carbon, and I found them very useful. Hopefully you'll find these quite useful. Common walls, and in fact, in our particular case, our common wall at the moment is the brick veneer from the base case, but in fact you can see we use primarily Colorbond and Abodo cladding there. Both of those have a lot less embodied carbon to them than the full assembly of brick veneer, pine studs, R2.7 plasterboard painted versus, say Colorbond metal cladding, 40mm top hats at 900 centers, reflective foil, 90 by 45 pine studs at 450 centers, R2.7. So a similar thing, but instead of brick veneer, it's now Colorbond. This one's the same, but it's shiplap pine, which is an approximation for Abodo there. And changing those in this particular design from standard brick veneer, we saved 9.4 tons of carbon dioxide compared to new brick veneer, if that's what we were going to choose. And I just put that in because that's standard construction in my neck of the woods. So let's put that on the tally. Choose low carbon claddings, 9.4 ton savings. And we're getting close to the end of my tally sheet here. Principle 11, last principle, choose companies who provide pre-offset products. And this is where I introduce Climate Active. Now, Climate Active, I did mention it before when I was talking about Wholesome. Climate Active is a government program that companies that have taken the time and effort to create EPDs for their products can then go to Climate Active, where they have some verified offset companies, and they can then purchase offsets through Climate Active, and sort of a more legitimate way with third-party oversight to do offsets. Now, I know there's a lot of discussion and a lot of problems with offsets that have come up in the last couple of years. So it's definitely something one should watch. But I think as a general rule, yes, we should definitely minimize our embodied carbon, do what we can to be, energy efficient and all of that first. But there will always be a leftover component once that process of efficiency is done. And we're going to need to have a robust carbon offset scheme. So at the moment, this is the best one out there. At least it's has some third-party oversight, but let's watch it over time. If you go onto a website, there's a link through to Climate Active, and it tells you how to filter through to building products. Now, there's not many on there at the moment, though the ones that are on there are really useful. You can see Wholesome, which I talked about before. The other one that I used on this particular project was Cineat. Cineat, their carbon offset product is called Optuact, and you simply ask for their standard plasterboard is called Master Shield Optuact. That's what I ordered, and that's what you get. And just again, just a specification, and now I've saved 3.5 tons of carbon dioxide because it's been pre-offset for me under Optuact and through Climate Active, similar to the way that Wholesome does it. And what I like about this, yes, we have to be careful of offset schemes. We do need to watch them, but I love the idea that it's not just the builder and the designer who have to solve the world's problems here. It's each product taking responsibility for itself and providing to site a product that is low or zero embodied carbon in this case, and that just leaves us to make sure that our homes are operationally under operational carbon neutral, and producing as much power as they use. If we can do that, that would be our little bit, and we wouldn't have to worry about the embodied carbon, which is why I particularly like this climate active idea. All right, so let's put that 3.5 tons on Cineat Optuact carbon neutral plasterboard, and we add that up on our little tally. And as built, we came in at 173.6 tons. That was a saving, an upfront saving of 40.1 tons. Now, of course, 41.1 ton doesn't sound big compared to 173, but when you think of 40 tons of a gas, that is a huge amount of a waste product that's going up into the atmosphere and leading to climate change. So I'm still reasonably happy with it. It'd be nice to go further. There are some things that we could have done that I haven't mentioned here, so I'll mention them quickly. One thing, we could have done Wholesome carbon neutral concrete, carbon EcoPack Zero to all slabs. We just put it into the beams and to the into the piers, but we're actually doing it on a job coming up where we're putting the EcoPack Zero triple blend into the slabs as well, and we're giving them a very light minimal grind on that as well. So I can let you know how that turns out, but I'm excited for that. Doing that on this job would have saved another 13.2 tons. We could have also used a Bodo, which was the lower cladding. We could have used a lower embodied carbon per square meter cladding. We could have used that throughout in lieu of the ColourBond. That would have given us a little bit of a saving, perhaps a little bit more maintenance throughout the life of the product. So whether or not to do that, but I put it down to show you the options. And lastly, as we mentioned right at the start, I think it was in that number 2 where we looked at house size and minimizing house size, we could probably have saved 20 square meters on this house, saving approximately 20 tons as well. And that would have taken it down to 138.9 and a saving of 74.8 tons, which is a lot in my books. But we managed to get 173.6. That was our total as built. So was that a carbon zero home? Is it a carbon zero home? Well, if we're looking at simple payback, 173.6 tons, and if every year I'm putting enough renewable power into the grid that it offsets fossil fuels being burnt to the tune of 10 tons a year, if we divide by 10 tons, gives a payback of approximately 17.36 years to pay back. So if we're just talking about simple payback, I'd say yes, it is a true zero home. What I particularly like about it is that's within the life of the panels. Panels warranted to last, at least 20 to 30 years. So that's within the life of that solar system that is making that power, which is quite nice. But should be applied everywhere. What you're looking at here is a graph of the different carbon intensity of the different grids in the different states of Australia. You can see up here, this is Victoria. We're a very carbon intensive grid, typically because historically we've been burning brown coal and distributing it a long way from Latrobe Valley down to Melbourne. You get a lot of losses there, and brown coal isn't very efficient at producing power to begin with. So it's been very carbon intense. So in Victoria, yeah, it works pretty well. But you look down here, here's Tasmania in the green. Green is Tassie. They're all on hydro. So it would take a huge, you won't get 10 tonne saving per year from similar renewable power being put into the grid in Tasmania, and you won't be able to pay back the system. So if you're looking for a way to offset your embodied carbon, once you've minimised the embodied carbon and you're down in Tassie, maybe you want to look at planting trees or some other way of doing it. So it's sort of dependent on where you are, whether this is a useful strategy. The other thing to note, if you average this all out, you get this line over here. And you can see for, the national picture is that we are decarbonising our grid. This is actually a really good news story. We are decarbonising our grid over time as coal-fired power stations, get mothballed, and wind power, solar power, and rooftop solar, come online more and more, and batteries come online. That is expected to get less and less. These are the projections, of course, out to 2050, magically becoming zero by 2050, just when we need it. Now, if this is the projection that happens and my home doesn't get to pay back to offset 10 tonnes every year because the grid's getting greener and greener and greener, so it's not offsetting so much, well, so be it. That will be a really good news story for Australia, so I'm happy to accept a fail on that if that is the case. But I think at the moment, at least I know on this Carbon Zero series, if I continue doing this, this way of construction, that the homes that I'm building are, trying to be responsible as they can for themselves and potentially getting to that true carbon zero figure. All right, let's wrap it up. So embodied carbon compared to operational carbon, which we looked at in the first part of this webinar last year. Operational carbon, we've pretty much cracked it. If you just design well, if you then build well so the house can perform to the energy rating of that design, if you then stock with efficient appliances and you put on some solar on the roof, the right amount, we looked at that in part, what is the right amount in part one, or what you should be aiming for and how to find that out. If you do that, we can pretty much solve or produce as much power over the year, over the day, well, hopefully over the day, as the house uses. But embodied carbon is a harder nut to crack. So here's some advice for building and design professionals. One is to follow the general principles that we went over today, and you can read them more thoroughly in step 2, as I've said. 2, support EPDs. So it takes a lot of money and a lot of effort for manufacturers to do these environmental product declarations. So we should be trying to use them and trying to promote products that are using them. And that gives a little bit of incentive for other manufacturers to come on board. It's sort of important that we get robust carbon data about how much embodied carbon is in products. So that's a really good thing to start doing, and start including products that have EPDs in your specifications. Support legitimate offset schemes, so like Climate Active and others, because we're going to need them. Though be wary and just check them over time that they stay legitimate. And check for product carbon changing over time as grids and supply chains green. Now, I mentioned aluminium before. Aluminium is typically an electrical process to create the aluminium. They use a huge amount of electricity, but imagine on a green grid. You know, aluminium could then be quite a low embodied carbon product if it was on a green grid. And aluminium is not even an element, it's an atom, it's one of the atoms in the periodic table. So it's pretty much infinitely recyclable, could become one of the greenest products in the future. So just as our grid's green, we should reappraise what materials we might want to use. And my wish list for government while I'm out there, in case someone's listening, we need a robust national coefficient database so that we're all using the same numbers and the same methodology, and we don't have those big variations in you know, when we're rating homes by their embodied carbon in those studies. And I know that the government is already starting that. Neighbours already has their beta version out, and I think that's the way the government is, or the industry is going to head towards the Neighbours pathway, perhaps instead of the EPIC database that I showed you today. They have different systems, and the Neighbours and different methodologies of how they calculate their data, and that Neighbours database works better with EPDs, which will help again spur the industry to use EPDs. So you might want to check out that. That is not yet linked in the website. I must include that. And I'd love to see embodied carbon included in NATAs. Not necessarily as a rating that we have to get, but it was an old component in one of the previous versions of the Accurate product that I use. They could reinstate that and start just getting a body of data of how much embodied carbon is in the cold shell of the homes we use. This will help us to look at how much embodied carbon is in different building types and potentially set benchmarks that we can then work towards with incentive schemes. And lastly, the government needs to focus on hard to abate sectors. As we saw, the industry, the electrical grids are greening over time, and some industries will just naturally, their embodied carbon will naturally green over time as the electricity greens. But there are hard to abate sectors, typically like concrete, where to create cement, you need to burn limestone. That has a chemical change to the limestone, and carbon dioxide is released in that change. So sectors where chemical changes just release greenhouse gases, those are hard to abate. And other sectors where they use process heat, high process heat, which are at the moment easiest and cheapest to do with gas. We need to put a bit of focus on using electrical ways of heating those and getting that technology going. So that's what I'm hoping that the government can start focusing on if they're not already focused on it. All right, and from this whole process, from trying to minimize the operational carbon and the embodied carbon, what are our savings? Well, dollars, as I mentioned before, approximately in the Ordinary Miracle prototype house here, it was around about $4,000 by the time you take into account charging the car and the gas meter and the amount of energy saved and the credit that you get on your bill. Nice pocket change to have in your pocket. Resilience, as you saw from the graphs, these homes, especially once they have batteries or electric cars, and that vehicle to grid integration is now in the standards. So hopefully we'll be getting vehicles coming out that can integrate with the house and can back up a house and potentially be the battery for a home in the not too distant future. So a battery combined with an energy efficient, low demand home really gives a lot of resilience if there are, you know, reasons that the grid goes down. Social benefit, such homes, you know, as we're trying to put more and more, not only all our homes onto the grid, but all our industry onto the grid, all our transport onto the grid, that's a big demand for the grid. We want to try and minimize the demand that our homes put on to minimize the infrastructure that we're going to need to make it all happen. So there's that social benefit of doing an energy efficient home. 10 tonnes a year carbon dioxide offset, at least at the moment. Hopefully that will go down as grid's green. Lower upfront carbon, at least compared to a standard home. You see 176 tonnes, still a lot. Yeah, still a lot. Hopefully we can do better, and hopefully product manufacturers will come out with more products with a lower carbon, which will help us get that down further. For this series, our low carbon series, and this particular house, a likely carbon payback. And maybe if you're in Victoria and you start doing something similar, you know, soon, you can get on get a payback while our grid intensity is still quite high. And probably if you're in the eastern seaboard states, it's going to be a very similar situation in Queensland, New South Wales, and Western Australia, similar carbon intensities. So you might get a reasonable payback or a chance of paying back the house over its lifetime there. And of course, a home that is built well and is designed to be energy efficient and healthy provides comfort and sanctuary. So, in summary, I'd like to invite you to walk what is a well-trodden path to a net zero home and potentially even a true zero home, and make your footprints positive. And that's my turn to put down the can. It's back to you, Ham.
Thanks, mate. Again, another incredible presentation with a ton of information. I think I'm probably going to have to go back and watch that again to digest it all because there's a lot to take in. I do have a few questions here. I know we're 15 minutes past 6, but I'm going to throw a couple at you, Jeremy, if I can. Just in regard to the transport cost of carbon, is carbon associated with transport in some cases also calculated in volume as well as weight?
Yeah, I don't have a graph on it, so I can't tell you, but I know that if something is high volume, it's not, you're going to need a lot of, maybe multiple trucks to transport it. So yeah, I can't really answer that particularly.
Yep.
But it sounds logical what the person's
It
suggesting in the question.
it does. It definitely does. Is offsetting allowed when following the greenhouse gas reporting protocol?
Well, now I'm not sure which particular protocol. You might be talking about the new protocols that have come in or are coming in for uh, big companies that have to start doing reports. But I know that their protocols are different from what I'm calculating here, and it's a different calculation methodology when we're calculating the amount of carbon in homes than for bigger industry companies that are calculating for their products. So I don't know the answer to that question.
And I'm going to just go through a couple more, and then we might wrap it up. I've got a couple of things to say before we go. And I actually think this one's from Brian, so he's going to throw you under the bus here. But who certifies a true carbon zero home? Are you going to retire and go and certify everybody's home in the next 40 years of your life, Jeremy?
Uh, no, and I wouldn't sell. And like, I hope I was quite clear and transparent that, I don't 100% know whether that home is going to be true zero, because it does depend on the carbon intensity and how that changes over time. So I wouldn't like to, say 100% that it's true zero. But the way to do this is to get feedback from the occupant. So post-occupancy evaluation is really good for the operational energy. That's how I got those performance from just the energy the house has been using from the operational energy use. And, maybe if someone was dedicated, a client might be able to tell you, give you some bills of 17.36 years worth of data. So the second part, the embodied carbon element, look, and until we have that robust national agreement on the methodology and the figures to use, and a way to do it, we can't really certify it. Look, you can get third-party people to do the rating for you, and I have done that, and I've used eTool in the past to find out how much embodied carbon is in my house. But to say whether the owners will use it in such a way that it will offset all its carbon dioxide through its operational energy gains is impossible at this stage.
And one last question.
And thanks, Brian, for that question.
Yeah. Can you please clarify the cost savings of $4,000? Is this outgoings over a period of time? And if so, how long, or on cost of construction?
Yeah, sorry, that was I went through it in the first webinar, so maybe you could watch that again. But basically, it comes down to you've still got my screen up, haven't you? Can I or not?
Do,
Can I?
yeah, you do. No,
Yeah,
no,
yeah.
you do. Yep.
All right, all right. I'm just going to flick right back to the beginning. Sorry, there's quite a few to go through. All right, here we go. So it comes down for this low cost living lifestyle part. Now I just got that particular figure from the fact that producing all this excess power and looking at the bills of this house after 12 months, this house is ahead $553 in credit. So that's what it says on their bill. You know, if they cashed in their bill, they'd get $553 for it. And you can, by the way, ask to get your credit back. I've got another client who periodically writes to the electricity company asking for their credit to be refunded. Right. Now, the average, if you look up what the average energy use for an average home in Victoria, that is, and a typical average home is dual fuel. So if you put the average gas use and the average electricity use together, you get $2,228. Right? So instead of paying $2,228, they're in credit 553. What's that? Let's add 500 onto that. That's about $2,800, say, that they've saved over the standard home. Now, not having a gas meter, you save at least, save around $1 a day not having the gas meter. So that puts it up maybe $3,100, something like that. And this house, as I showed in the first webinar, this house also charges its electric car at the house primarily most of the time, and it was able to show that it did 800. It produced enough power to offset the equivalent of $800 of petrol for a standard car. So you sort of put those things together, and that's how it came to close to $4,000 there. Now on top of that, which I did.
Sorry, it's 4,000 per annum. Then is that
Yeah.
I think?
That's 4,000 per annum. Now you could add on to that. This house also collected its own water, so that means that it's drawing less water from the mains, and so it gets charged less on its water fee. And because the sewerage fee is also measured as in how much you draw in from mains water, you save a little bit there. So there's little bits and pieces of savings, but I'd say around that $4,000 mark in this case is about right.
Awesome. And look, I definitely encourage everyone to jump on the SBA website and check out part one. I am going to wrap it up here. Jeremy, thank you again. I'm always blown away by how incredibly knowledgeable you are, and then just explaining it to our audience and myself in terms that I can even understand. So that's fantastic. Again, thanks for everyone for joining us today. Again, big shout out to Wholesome for sponsoring today's webinar. Don't forget, episode 36 is out of the Sustainable Builders Yak podcast, where Simon and Brian are chatting with building biologist and biophilic designer Fiona Gray. Now, events for 2025. We have every single event planned for the year, and it's going to be a mixture of online and in person. There's going to be some hands-on events, so practical events. There's also going to be, I guess, lecture-based events as well, the mixer events, and there's going to be a couple with a major partner who is coming on board, and that is an incredibly exciting partnership, which I can't talk about now, but I do believe maybe keep an eye out over the next 24 hours because that might be getting announced very, very soon. So thank you, Jeremy. Very much appreciate you coming on again today. I know you were unwell over the last 24 hours, and good to see you sitting at the desk. So everybody, thank you. Keep a lookout. This is going to go on our YouTube channel and will sit on our website, www.thesba.com.au. Thank you, everyone, for joining us. Catch you, Jeremy.
Thanks, Ham. Thanks, everyone, for joining.